Alright, this is where we left off yesterday, if y'all find this slide for me. So, one of the things that students always get confused is the difference between a physical property and a chemical property, and then a physical change and a chemical change. Okay, so I want to try to do my best today of trying to get you guys to understand the differences between those two things. Yes, sir. Huh? Oh, we'll get to that. We'll get to that today. Okay? Alright, so physical property is a characteristic that can be observed or measured. So let's start right there. So it's a physical property, something can be observed or measured. If I asked you guys to give me a physical property about yourself, what is something that I could observe or measure about you? What about your feet? Okay, I want to just look at your feet. That's kind of weird. But yeah, the size of your feet. Anything else? Skin color, eye color, hair color. You can observe it. Facial hair. So you guys kind of understand. Those are physical characters, physical qualities about someone or something that I can observe or measure. Your height, your weight, all of those things. Okay. But a physical property is that, but I can do those things without changing the identity of the substance. So if I measure your height or measure your weight, it's not going to change anything about you. It's a thing that you can actually measure or observe. Okay. So two examples of a physical property is the melting point and the boiling point. Okay. And we'll get a little bit more in depth in just a second because those two things confuse most students when they first hear it until they understand the reason why it's a physical property. Okay. So what is a physical property we've talked about, and then what is a physical change? Now what does a change mean? Is it different from what it was before? Yes, but here's the most important part. There is a difference between a physical change and a chemical change. Yes, we're changing it, but there's an important relationship that you have to understand about that change, and this is what it is. A change in a substance and this I would highlight this, that does not involve a change in the identity of the substance. Okay? So when you change it, is it still what you started with? Yes. So if I go outside and I cut the grass, is it still grass? You just made it smaller, right? You made it shorter. If you cut your hair, it's still hair. You just made it smaller. If I grind salt or pepper, it's still salt and pepper. You've just made it smaller pieces. Okay? So those are easy to understand. Okay? If I go out and I chop wood, is it still wood? Yeah. So all of those things are easy to comprehend. It's still those substances. But the two that really throw people off are these last two, melting and boiling. Let's start with the easy one. If I take a cube of ice and I set it out on the table and it melts, what does it do? Turns from a solid to a... But my question to you is, what did it originally start out as? What chemical? It started out as water in what form? The solid. When it melted, is it still water? It just changed states. It changed from a solid to a what? Liquid. That's easy to understand because you can see it. So it did not change the identity. But here's where people really get confused is this last one. Boiling. When I boil something, what does it go from and to? Liquid to a gas. But here's the important question. When you boil it, it goes from water to what? Water vapor. Is it still water? Yes. The problem is can you see it anymore? That's the difficult part. So people assume that when something just disappears, that it's no longer that substance. Okay? But the reason it's still water is we've just changed its state of matter. So even though melting and boiling actually change the physical appearance of it, because do you agree? If you grind salt and pepper, does it still look like salt and pepper? If you cut a piece of wood, does it still look like wood? But when you melt water, does it look the same as it originally started? No, when you boil water, does it look the same as it originally started? So that is why these two things are very difficult for people to understand. Okay? Do what? Seriously? Yeah. It's water. It's just in its solid state. But what is ice? Underneath those two, write that down, please. I know it's kind of hard to see towards the bottom, but it says change in state of matter. I harp on this because it's important, and I've been doing this for 5 years. And every year, the same mistakes are always made. People always jump to the conclusion, oh, boiling, you got to heat that up. That's a chemical change. No. Is it still whatever you boil? Yes. It's just changing its state of matter. You're changing it from a liquid to a gas. Okay. So a change in state of matter is a physical change. Okay. So again, one more time. Big, huge, bold letters. A change in a state is a physical change of a substance from one state to another. Now, what are the 3 states that we most commonly talk about? You know, there's solids, liquids, and gas. The weird one is the plasma. This is going to be the only time all year long you're going to see this. I don't ever talk about it. We don't ever need it. We don't ever use it. But what is plasma? And I know you're going to ask. We'll talk about it in just a second. Okay? We're going to come back to this in one moment, but I want to talk about these 3 things for just a second. Hint, hint, wink, wink. Make sure you know how to define these 3 states. I would know these 3 phrases. Okay? You know them, you just don't realize how to put them into words. Okay? A solid has a definite volume and a definite shape. Okay? How do you calculate the volume of a perfectly cubed object? Length times width times height. Can you calculate the volume of a cylinder? If you have the right formula, the volume of a sphere, the volume of a pyramid, the volume of a cone, all those things, right? All those geometry formulas that you've forgotten by now, just like I have. What if it's an irregular shaped object like a rock? Water displacement, very good, okay? And it has a definite shape. I mean, I know that rocks don't have, like, perfect shapes, but it's a definite shape, okay? You can actually recreate it 3-dimensionally. In the liquid state, matter has a definite volume. You can pour it into something and you can measure it, but it has an indefinite shape. Liquid has the ability to do something that doesn't allow it to keep its shape. What does it do? That's a very unscientific term, but you're right. AJ, does that sound better? It flows. Okay, it swishes around. It flows. Same concept, a little bit more scientific. It has the ability to flow. Okay, and what that simply means is the atoms can just roll on top of each other without impeding its flow. Okay, do some liquids flow better than others? Does anyone know? Thank you. Very good. Viscosity is the term of the ability of a liquid to flow. So like if you pour syrup, it's a little thicker, so it's more viscous, if you will. Okay? And then finally, the state of gas has neither a definite volume nor a definite shape. This is kind of weird, but I need you to think about just gas in nature. Can you trap a gas into a shape? Absolutely. But in the room right now, are any of those gas molecules forming into specific shapes? No, they're going wherever they want to go. Okay? Now, you can confine them to a specific volume, but if you open up that door, can they leave? Yeah, they can do whatever they want to do. They're not contained to specific shapes or specific volumes. So, finally, the last question is, what is plasma? Plasma is a high temperature, physical state of matter in which atoms lose most of their electrons. I would highlight that. Atoms lose their electrons. So give me an example of what you think plasma would be a part of if it's high temperature. No. If it's high temperature, it would melt your skin. You're thinking about, no. The sun. Anything else? That is the sun. Lightning, fluorescent vapor lights, the sun, other stars, and then aurora borealis. What's another name for that? The northern lights. So here's what the northern lights is. Okay. So what the northern lights are, and these are real, they're not fake, is when the gamma radiation from the sun enters our atmosphere. There's so much energy in that gamma radiation that when it hits the air molecules in the atmosphere, it knocks the electrons off the atom. Like, that's how much power the gamma radiation has that our atmosphere is actually protecting us from. So when it hits those oxygen and nitrogen molecules, it strips the electrons off, and when those electrons jump off the atom, they give off light. We'll talk about more about that later, but that's where the light comes from. I don't really know. I mean, what do you mean go through it? I've never read that, but sure. I mean, I see what you're saying, like the gamma radiation, but probably more than less. Yeah, sir. It is because the ozone's there protecting us, but it's not a good thing for the ozone. No, it was beautiful, but it's not a good thing. Okay. All right. Also, I would put a big circle around this box, around this slide. You are at some point going to have to draw the states of matter. Okay. And that's your perspective of the microscopic, or if you want to call it the picoscopic version of how the atoms are related. So basically, solids are perfect shapes, and they have definite volumes. You can calculate it. Liquids are a little bit more spaced out. They have a little bit different function. And then gases, what do? Go wherever they want to go, right? They're not confined to a space or confined to a volume. And then the plasma, which again, today's the only day you're ever going to hear about that. What do you think the red positive things running around are? The nucleus of the atom. Very good. Okay, and you can barely see it, but the green circles have negative signs, and those are the electrons shooting off into space. Do y'all have that slide right there? Okay, do me a favor. This is going to look kind of weird. Let me do it in green. Okay, so kind of make a line like this with an arrow, and write the word light. Yeah, kind of a squiggly line, and it is squiggly for a reason. Whenever you ever see light drawn, it is drawn in a wave-like fashion. Okay, so whenever electrons are ripped off of an atom, what do they produce? Light. Keep that in mind. We'll come back. There's your Velcro ball. Okay, so let's go back up here and let's read this paragraph. Now, there's a reason I'm coming back to this, because I want to talk about the difference between a physical change and a chemical change, and this is going to kind of parlay us and go into chemical, because remember, the definition of a physical change is this is a question, is the identity changed or remain the same? It remains the same. Okay, so Joseph, do you mind reading this? And I'm going to pause you a few places, okay? Pause right there. That just said, if I take salt, what does dissolution mean? It dissolves. If you pour salt into water and stir it up, will it dissolve? Yes, okay. But this just said, if you dissolve it, you can recover the salt from the water. How would you do that? Boil it. Why does boiling recover the salt? Okay, so all the water leaves, and what's left? The salt. Does that make sense? So keep that in mind. So even though we pour it in and it dissolves, we can get it back out by boiling the water back out. And what will be left is the salt. Okay, keep reading. Pause right there for me. Here's what I want you to do. Above or below this slide, wherever you have the room, please draw this for me. And draw it just like this. Now, this is a weird way to do it, but I'm emphasizing something when I drew it like this. Does anyone know what that line between Na and Cl represent? A bond. Okay. Here's another little Velcro. Does anyone know which bond type this would be? By the way, Teddy, this is going to make you really bad, or really mad. A hydrogen bond is not a bond. We'll talk about that later on. Okay. So, NaCl, when we mix it with water, it will dissolve, right? Okay. Here's what it just said. Reread that big, bold sentence you just read to me in all caps. Here's what they separate into. Write it just like that. Na plus and Cl minus. What do we call things that have pluses and minuses on them? Ions. Very good. These things are ions. So here's the deal. When I take that sodium chloride and I pour it in the water, it's going to separate. It's going to dissolve. It's going to turn into ions. Keep this in mind as he reads the next little part. Okay, Joseph, I'm going to flip back. Everybody got this? Go ahead and keep reading. Very good. So here's what I want you to think about. Remember, a physical change is, does the identity of the substance change? And a physical change, no. Let's go back and look. Does the right side match the left side? It looks very different, doesn't it? However, is anything new created? No, all you've done is just separated those two things into its ions. But here's the reason why we can also classify it as a physical change. In a chemical change, if a physical change doesn't change the identity, what does a chemical change do? It does change the identity. If I take a piece of wood and I set it on fire, can you get it back? If I take your hair and I pour bleach in it, can you unbleach it? Can you unbleach it? No, you can't unbleach it. So here's my question. Can I recreate the salt that I dissolved? Yes, you just told me. How do you do it? Boil it. So even though technically I changed it, is there an ability to get it back to what it originally was? Yes. And that's another reason why we consider this a physical change and not a chemical change. Okay? So even though it's changing its state of matter, which again is a physical change, it's still not chemically any different because we can reproduce what we originally started with. All right, so that's going to get us into, actually, right here. There's one thing I want to talk about. Is everyone look at the solid water, which is known as what, Jordan? Solid water is known as ice, and liquid water is known as water. Okay? Do me a favor. Which one of those two circles would have the greatest density? Remember, density is the amount of things packed in a certain amount of space. Are both of those circles the same size? Which one has more stuff packed in that same circle? The liquid does. How do you know, physically, like you've experienced this, that ice is less dense than water? It floats. This proves it, based on this picture. Now I know what you're thinking. Wait a minute, ice is a solid. How in the world is it becoming less dense? And there is a reason, and we'll talk about it later. And it's the way that the water molecules have to form to each other when they turn into a solid. So when they freeze, they actually separate just a little bit. When they freeze. Because what's freezing? What's freezing? So movement, the molecules slow down a little bit, and when they slow down, they start to, when I say orientation, do y'all know what I mean? It's how things are arranged or degree turned, okay? The orientation of the atoms or the molecules change themselves, and so it creates these little bitty gaps and tiny spaces that makes it have the less dense state. That's exactly why it expands. That's exactly right. So when you take water and you put it in the freezer, the reason it expands is because those molecules actually space themselves out to a degree. So that's exactly why it expands. Yes, ma'am. Okay. All right. So here's the thing about, and this is a weird word, but changes in states of matter are bidirectional. What do I mean by bidirectional? They go both ways. So can you go from a solid to a liquid and a liquid to a solid? Yes. You can go from a liquid to a gas and a gas to a liquid. You've grown up hearing most of these words. Come back to you. There is two that we've left off. Okay? And again, this is bidirectional. Okay? So I need you to add this for me. it is possible to go straight from solid right into a gas. What is that called? Sublimation. It's the process of subliming. You're right. Okay. Sublime is the action, is the verb. This is the process. Okay. Hold that thought. Does anyone know what actually goes through sublimation or sublimes? Dry ice. Okay. Now, a lot of people don't know what dry ice is, and Teddy, you said it. What is it? Very good. It is frozen CO2. So that stuff that you breathe out, they get it cold enough where it actually turns into a solid. Okay? Well, think about that. Carbon dioxide normally in nature is in what state? A gas. So what happens is if you take that dry ice and you leave it sitting out on the counter, it's not going to puddle up. It will turn right into a gas because that's what it is at room temperature, which is what we would be having there. Okay, so sublimation is the process of going from a solid to a gas. Yes, sir. You can actually buy it at Publix. You have to be 18 to buy it, though. It is cool. Here's, and I do mean this. Like, you guys are, that's kind of silly, but for real. If you touch dry ice with your bare skin, like if you hold it like a regular ice cube, it will burn. And I say burn, and it's like a freeze burn. It'll kill the skin, so it really is kind of dangerous. And you don't put it in your drinking water because it's putting carbon dioxide in your water, which is toxic. So don't do that. Okay. I will tell y'all that dry ice is used for packing because it stays colder longer. So like if you have to travel a great distance and you want to keep something really cold, use dry ice. But again, don't put it directly on the food. You want to kind of put a towel between it, but it'll keep the environment colder longer. All right. Am I? It's a myth. It's a myth. It's a myth. It takes it longer to boil. That's a myth. That's not right. It stops it from boiling. Okay. All right. So, sir. Deposition. Yes. Very good. Actually, what Joseph just said is very good. I had it up here. Remember I said it's bidirectional. It goes both ways. So from a solid to a gas is called sublimation. But the opposite, again, you don't have to write this unless you want to, but a gas straight into a solid is called deposition. It's a very rare thing. In fact, I can't even think of anything off the top of my head that actually goes through deposition. It goes straight from a gas right into a solid. But deposition is the opposite. Stop. Like, it's not funny anymore. Okay? All right, so chemical properties. Again, a chemical property relates to a substance ability to undergo changes. So again, we're talking about the ability to change that transform into different substances. So the key there is this ability to change to different substances. Some things change very easily. Some things are harder to make them change. Some things go naturally. Some things you have to force them to change, and we'll talk about that. So a change in which one or more substances are converted into different substances is called a chemical change or a chemical reaction. And so this is what's important about all of these things, is that when you get into chemical changes, you get into chemical reactions. Okay? So go ahead and make sure that you know these two things. Reactants react. Duh. What side of the reaction is it on? The left. The left side. Now, I'm going to go ahead and show you this, and you're going to see this a lot. This is my shorthand, and you will never see me ever write the entire word reactants. Okay, so right here, my shorthand for reactants is RXTS. Reactants. Kind of like prescription is RX, right? Doesn't make any sense. My shorthand for product, it's RXTS, Teddy. Okay. Now, products are the substances that are formed, and they are on the right side. So reactants react, products are produced. Okay? So in this reaction, we have carbon plus oxygen yields or forms carbon dioxide. Here's another curveball coming at you for just a second. Do me a favor. Do you guys notice something odd about that right there? Say that again? Thank you. Very good. Write that underneath that. If you didn't hear what she said, this is what she said. Diatomic. What does diatomic stand for? Two atoms. Well, look at what you have down there. What is O2? Two atoms. Does that make sense? Two oxygen atoms. Okay. I'm going to go ahead and tell you this. I'm not going to tell you all of them right now, but there are 7 diatomics. There are 7 of them. Who is one of them? Oxygen. Oxygen is a diatomic. And here's what a diatomic means, is that it would rather be with its twin than by itself. And I know that sounds really weird, but what does it mean by its twin? The same thing. Okay? So it would rather be with its twin than by itself. And there are 7 of them that act like that. Okay? This is the biggest slide out of the chemical chain. So put a big circle around this entire slide. Okay? There are 5 signs. Okay? 5 signs of a chemical reaction. And what I mean by that is that it's something that your eyeball can see. Okay? So if you can't see one of these 5 things with your eyeballs, then it's not a chemical reaction. Now, the problem is you only see 4 pictures. So let's talk about what the 4 are so far. The first one is when you have bubbles. So if you want to write bubbles anywhere on this, it may be easier instead of highlighting that because I know it's kind of a small picture. Bubbles tell you a chemical reaction has occurred. Now I have a really dumb question, but it's a really important question. What is a bubble? It's a gas trapped in a liquid. That's what a bubble is. Okay? So if you see bubble, it's a chemical reaction. The next one, this is a weird one. A solid, let me change the color so you can actually see a little bit better. A solid precipitate forms. A solid precipitate. Now here's the weird part about a solid precipitate. As soon as you hear the word solid, you think that when I pour 2 things together, it falls out like a rock. That is completely infactual. It is very small, little baby, tiny particles that are floating around. How would I get those particles out of that solution? Give me a better word than strain. Filter it. You take a coffee filter and you pour it through a coffee filter and everything will be trapped in that coffee filter. So a solid precipitate forms, and we'll talk about how we get solid precipitates. The next one is heat and light. Heat and light. And finally, the last one is a color change. Excuse me, that's number 4. And the 5th one is oxidation. Say that again. What? Really what that is tanning is a change, it's a darkening of the pigment of your skin. But you got to think about the pigmentation of it. It's a good question. I would say yes, because it's a color change based on the pigments in your skin absorbing UV.